So let me move here. So now we have a skeleton of a single neuron. I'm going to abstract it here in terms of a graph. So I have branches here. They converge to a node. Converge to a node meaning that they're going to be summed. And then I have a line here. So look at the thing in the dotted box here. That's a single neuron because you have all these branches. Every one of these branches is going to have a weight associated with it, and it's coming from an output of another neuron. So just replicate those things. So there's neuron J, the output of neuron J, and feed into, by this weight, is going to weight this to coming one input, and then you have another input. All these things are going to be netted or summed into this one neuron. Phi represents the cell body nonlinearity. It's going to be a phi of what comes in. We use V sub k here. And then the output here, this nonlinearity, in this notation, we use Y sub k for the output neuron. So this is neuron K, neuron J, and you could have, and think of a cascade, linear cascade. So this is an element, maybe an array or a vector of these guys, and this another vector. We just zooming in and looking at one particular neuron. And so this single neuron, mathematically, we can express it. We're trying to create an efficient graph that represents the information for us. So if I look here, oops, sorry, I'm doing all these things and I need to. So Y sub k is really a nonlinear function of a weighted sum of all the incoming signals from the other guy. And by the way, on the outset, notation. Different books, different references use different notations for variables. So sometimes you have W for the weight, which is almost universal, but not always. The signals, sometimes V sub k, sometimes U sub k, sometimes X sub k. So I hope you can overcome the issue of having varied notations all the time, which means you have to be patient a little bit, look at what the notation is, and make sure for whatever you're reading, what the notation, what represents. And there's no way out of it because every textbook, every reference uses a different notation. So I apologize for this, but I can't do anything about it, okay? So then the main thing here, if we're focusing on a single output, in supervised learning, sometimes referred to as error-correcting learning, you have an output signal, and you have a reference. In this case, the reference is referred to as D sub k for desired value. Sometimes the label for L, whatever, Y sub k. And you have an output here, which could be Y sub k in this case. I noticed that in coding, often people use Y sub k as the label, and sometimes use the nonlinearity itself, whether it's phi or h, as the output of the neuron. So whatever you're reading, it pays to sit down and just make sure you get the notation in an ordered fashion so you can understand what they mean by it. But the idea is that supervised learning and the error-correcting learning, you have a label and you have the output. Now, notice in this case, we're suppressing any reference to a stochastic process. We're trying to simplify. Because what they do, obviously, we're thinking about everything as random variable, stochastic process, but when you do the learning, often what you do, you apply expected value. The minute you expected value, basically everything becomes deterministic. So you'll see in a second that where we apply things as a random variable, we apply the expected operator, and then basically look at the deterministic process. So the learning is we're going to look at a way of incrementally changing the weights to achieve an outcome. By no means gradient descent is the only method, okay? However, if you look at all the libraries and every reported, the skeleton of the learning algorithm that's been working very well in the libraries we have and the applications we have has been based on gradient descent. And gradient descent has a lot of different variants. People have been working hard to have some wrinkles here, wrinkle there, to modify it and make sure that its performance, convergence, and what have you is better. But the core technique is really gradient descent, which hopefully we'll walk through in a simple way today, and we'll be revisiting it as we move forward. So the question, does anyone know how to get rid of this one quickly, or should I just wait for it?
Just get the two arrows going together. I think
Is that right? Okay. This one? It goes away? Oh, no. Okay. Sorry, I think it's... Okay, so we'll just... You recorded, by the way. So the bottom line is that... let's see if we could get this guy. So here is, so what it is, training data, evaluation, testing data. Here's just a zooming in on one particular neuron, and that neuron output is having this. This applies to every neuron, arbitrary neuron structure network. And we're going to think of a feed-forward neural network. And later on, by the way, when you use matrix and vector calculus, it becomes much more compact and often much better, but traditionally people have started with the point-wise, kind of element-wise analysis. So the key thing is you have a weight, and for the gradient descent you need to initialize that weight. And you'll see in examples later that when we have the so-called error-correcting learning, which tells us that we need some cost function, or we need, the word cost, by the way, cost function or loss function is interchangeably used. Typically, people nowadays use the word loss function, but you can say cost function as well. And you say a performance index, a lot of different words that people use depending on the discipline. People favor a certain word over another. But the one that's favored right now in so-called deep learning and neural network is really the loss. Loss represents the cost function. And once you have that loss, that guides you to basically incrementally change the weight from your initial guess. One thing that we'll see initially that these networks, by virtue of having nonlinearity and multi-layerism, leads to optimization problems that are not convex. So they're not convex problems, which means you have many local minima. And your job is to try to minimize some cost function. And that cost function, when you minimize it, you'd like to go to a minima. Clearly, you'll go to a local minima. But if that local minima is not good enough for your error criterion or performance, you have to either reinitialize or you have to do something about changing the stepping rate. And we'll walk through these things later on. But the point is, you have some guess, you want to incrementally steer that guess, and you have a change at every step of iteration. This change of the weight that I have represented here, the question mark is what criterion do I need or can I use to perform this change at every iteration, at every in-sample, every incoming data, every data I measure. You have an input data, you have a label. You're going to use this information to help you suggest or recommend a change by this guidance of, for example, gradient descent. So, I'm confused here. So a simple supervised learning method. Where did I don't know if I missed. So basically what it is, you have here is the component. This is a parameter associated with neuron K coming, signal coming from another neuron called J. This is, you initialize this weight at time or sample or step N. And here's the change. And you add the change, and that gives you the next parameter update, which presumably is going to minimize an error, minimize that loss function for you, which means over the training data is going to have a better performance. Any questions?
Could you state again what the subscripts K and J are?
Oh, and this thing here, K, is associated with the neuron, kth neuron. And the J is associated with the incoming signal, jth neuron coming from another one. So these are indices, and every neuron K is going to receive many of those things. So J and K, they're going to row through indices. Okay? So for example, the output of the kth neuron, here's the desired value of the output. We make in this case, we have a difference. This is error correcting form. And we have an error signal. And this error signal, we're going to convert it into a loss function. One way of doing this is to using the L2 norm, for example. And in your linear algebra section, you're going to see all these different norms. We know there's many norms, P norms. We have L1, L2, L infinity. All these norms have different characteristics and very useful. Traditionally, people have used the L2 norm in signal processing and engineering historically, in machine learning, L2 norm. But more recently, there are other different loss functions that people use. There's the cross entropy methods, what have you. We'll come to those other fancier techniques with some advantages. But this is the basic historical L2 basically norm. So this one, you square it, and you sum all the errors at the output, that gives you an L2 norm, square. And you define a cost or loss function, and here's the square of the errors. You sum them over all the outputs that are of interest to you. So you can either have a cascade, modular, organized network, or you can think of a population of networks. And I have a set K of these networks. These are the outputs. And I'm interested in the outputs, and I'm basically defining an L2 norm square. You put the 1/2 here because it's going to make the calculations easier. And you really observe this one, E here stands for expected value. Because really the underlying processing here is all statistical. Okay, we use the deterministic stuff to be able to compute things precisely and what have you see it. But we should always keep in mind that we are dealing with random variables, random signals, and that the training, we need this randomness to represent the real data. Because the training data is just a chunk of data that's available to us. Presumably, it's representation of the true data of the problem we're dealing with. If we're dealing with faces, they come in all variety. But when my data is going to be a finite set of those faces. So I don't want to be tied into this particular data that I have available. I want to learn faces. So I'm going to view this data as random variable, which means it's an ensemble that represents statistics of all the faces. Okay? So here the expected value operator, but the minute you hit it with a expected value, it's going to turn this whole thing deterministic, right? Because expected value operator is a linear operator. It walks through and basically have the mean of all these different values. When you look at the error, you're looking at the mean of the error, okay? So the so-called stochastic gradient descent on this side, which we have the expected operator, we can actually just, for now, view this one, this expected value. Sometimes, so if you notice, I have this stuff here, which is the same thing, and I replace the expected value by a summing of all these different values and dividing by n. So this is an averaging. We converted the expected value in an average. And this is only valid if the data is so-called ergodic. So if the data, stochastic data, is ergodic, the word ergodic translates from statistics is that you can represent, you can change or replace the ensemble average or mean by the time average, okay? Or the sample average. So there's an ensemble and there's sample, okay? So that's what it is. And hidden in this notation, if I want to apply statistics, say, what does it mean when I apply expected value to some quantity? If the quantity is continuous, that's going to be the integral, which translates in discrete to a sum of the probability density, or the probability times this variable. So if the probability density happens to be uniform, which means all of them equally likely to occur, then basically you view this 1 over n that we have here, if you put it inside the summation, this 1 over n is like saying the probability density for this data is uniform. All of them have 1 over n. So that's what the ergodic stuff is, that we assume, if we don't know any better, we select basically all of them equally likely to occur when we adopt or enforce uniform statistics. And now we have on this side here, in mathematical form, things that deterministic, because we replace the expected value by an average, right? And we can always view this one average. For the calculation, we can look at things without the average, do the calculation. We keep in our mind that we're always basically going to seek an average of this quantity, okay? So if I want to crank out the calculus, gradient descent, for this quantity that I have here, which is really the same quantity here without the expected value, which is just, and I say, what's a gradient descent? Gradient descent, and we'll walk into some definitions of gradient descent later, could be represented by the partial derivative of this E, which is a scalar quantity, the norm is a scalar quantity, with respect to the parameter of interest that I need to update. The parameter of interest here, each one of those WKJ. If I put a negative sign here, that says I'm looking at gradient descent. So without, okay, if I put a positive sign, I'm looking at gradient ascent. And this quantity here represents a change, the maximal direct of change of the cost function, okay, that you need to move towards. So I start with some initial guess, and you apply this data, and you crank out this gradient, and the gradient tells you, you better make the change along this direction. It gives you the direction of the maximum change. And this will represent the change. Now, because this change is discrete, not continuous, we insert an eta parameter here, which means I want to control the size or the amplitude of this change. The change gives you a direction, right? But the amplitude, how much change, is critical. So imagine that your energy surface is hills and valleys. You're standing somewhere, that's the initial guess, and then you need to move. If you go on gradient descent, you want to follow the direction of the maximum descent. Now the next step is, what is the stepping? You're going to have a large step or a small step. So that's what the eta is. The eta controls the size along that direction, the length along that direction of stepping. If you step too large, if you have a step, you may actually miss some local minimum. You overstep it. You see some examples of that. If you have steps that are too small, you're guaranteed to move along the gradient descent, but you may take infinitely long time. So it's a trade-off. It turns out, when you do in the training, and I'm just giving you this one as a shout out right now, sometimes on purpose you increase the eta, which is the stepping, because when you initialize the system, it initializes on a bad location. there's no good minima nearby. You're going to converge to a lousy minimum. So sometimes when you initialize it, you make the eta, the stepping, so large. You make it random stepping until over time you go to a region in the landscape where you can have good minimum. And what's a good minimum? It's controlled by the accuracy performance. So sometimes you have in the training, you initialize things and you don't get any good performance, just get stuck. And you keep training and nothing happens. Why? Because your initializing was poor and you get stuck in a bad region of the landscape. So what most of these techniques do initially, sometimes they like the eta or the stepping to be very large initially, make it almost like random stepping on the energy surface or the loss function or the valleys and hills, until over time, statistically, you come to a region that has good solutions. And there's some concepts from physics related to that, which is called annealing. And physical properties, sometimes they heat up some material, okay, and they do a staged cooling. So you have it very large and you stage cooling until you have the best kind of material property that converged. So the step from here to here is written in basic calculus. We use the chain rule. And this is in a scalar format. This is an undergraduate material. You have a scalar quantity. This E, as you can see here, is a function of a given constant D and the output. And the output is itself a nonlinear function of the weight and the input. So you keep taking derivatives. This is the derivative you want to compute. You break it down into derivative of E with respect to E sub k, epsilon with respect to E sub k, and then E sub k with respect to the output Y sub k, and Y sub k with respect to the input to that neuron, which is here is denoted as V sub k, and V sub k with respect to the particular weight of interest. So each one of those things you can compute easily by tracing what this quantity is. So the first term here, when you look at the definition of this quantity, the derivative of this with respect to E sub k, it's going to give you E sub k. E sub k with respect to Y sub k is going to give you just -1. And this third one is going to give you, because there is a nonlinear relation we call phi, it's going to have the derivative of some nonlinearity, whatever your nonlinearity is. And then V sub k is the one that's directly, V sub k is equal to the W sub k times kj times xj, gives you xj. So this chain rule spits out for you those terms. Then you collect all these terms and you have an expression for how to guide the change of the weight, which is going to have E sub k times derivative of nonlinearity and x sub k. Any questions about this? Basic scalar calculus in this case. And you can do this one all in a vector calculus. Any questions?